Hi, in this lecture I'm going to discuss how we would study the equilibrium of non-ideal solutions. In the previous lecture we introduced the concept of fugacity, and this is particularly useful when we come to the equilibrium of non-ideal gases. And here we want to look at a more general concept, and it's called the activity. And the activity is useful for studying the equilibrium in liquids, such as in a cast, for example, or in the case of solid, then we will have an equilibrium between the liquid and the solid. So to do that, we're going to start from the relationship between the chemical potential and the fugacity in solution, and then we'll introduce a few concepts about the deviation from ideality. So let's look at it here, and let's start by looking at what we call remember in the previous lecture we talked about residual properties, which were the difference between the non-ideal and the ideal properties. Here, since we are in solutions, we'll use a very similar concept, and that's called the excess property. So I'm going to define the excess property, M excess, as the difference between the property of the real solution minus the corresponding property of the ideal solution. So since it is not a gas, then we just use the superscript ID. For example, if we're looking at the excess Gibbs energy, G excess, it will be the difference between G for the real solution minus the corresponding G for the ideal solution. And if we multiply here by N, the number of moles in the system, then we would have correspondingly the differences. The reason we multiply by N is that I would like to now look at the chemical potential of a non-ideal solution and the chemical potential of an ideal solution, and take the difference and look and see how we can characterize this difference through the concept of activity. So here I will say that if we have, we introduce also the concept of partial molar property. So partial molar property is defined in general to apply to any property. So let's just define it first. Here, let me just write it correctly here. Molar property. And this partial molar property for any property M for an element I in solution, if we put a bar on top, this is just an indication or a symbol that it is a partial molar property defined as the rate of change with respect to the concentration of element I of the total property for the entire system, N times M. So with this, we can say that Gi partial molar is equal to d by dni of the product of N times G. So all of these are just preparations so that we can, in fact, evaluate the difference between these two quantities that we have. So we wanted to eventually kind of look at the difference between the real and the ideal solutions. So with that, let's just now clear the page here and then start to discuss the specific partial molar Gibbs energy for an element I in solution. So this will be Gi in solution. So we have here Gi and that is in solution. So this is excess in solution. We defined it now as equal to d by dni of ng excess. So this is the excess Gibbs free energy, and that is the difference between the real and the ideal. So the real is d by dni ng, and the ideal is d by dni of ng. Now I'm going to use id. Now the first term here is by definition the chemical potential of element I. So this would be mu sub I. And now the second term is by definition is the partial molar property of element I, which is bar, but it is ideal. So it is an ideal. Also, we can look at the first term and give it another symbol, which is the partial molar property, free energy of element I. So this will be Gi partial molar minus Gi ideal partial molar. And therefore, we would see that the chemical potential is the same as the partial molar Gibbs free energy. Both of them are interchangeable. Let me just kind of remove myself so you can see now the total picture that in here. So what we're going to do is that we will start from the differential in the chemical potential of species I in solution, relate this to its fugacity in solution with the hat on top, and then we will integrate this between two states. One of them is a reference state and one of them is a current state, and we'll do that for the ideal gas, for the ideal system, and we'll do that also for the real system. And the changes or the differences that we will have, we plug them back in here and define the activity in a way that we define the fugacity coefficient before for gas systems. So let's do that right here. If we clear the page, and then we will now, we know that the relationship between mu and the fugacity has been defined before as RT d ln of the fugacity, but the fugacity is in the solution, so I give it a hat here. And now I want to integrate this differential between two states, one that is reference and the other one is a current. So let's say I want to do integrate between two states, and I'm going to do state 1 is a reference state, and this reference state we will have Gi bar is equal to Gi 0, where Gi 0 is the reference Gibbs free energy, and Fi hat in this case is in the reference state. It will be unmixed, so it will be Fi. So this is unmixed reference state. So this is state 1. And now let's look at state 2. And state 2, we can do that by defining state 2 as a current state. And the current state is, we have a solution now. It's not unmixed, so we have a solution. And the solution has concentrations of species Xi, and also it has a fugacity of each species Fi hat in solution. So if I look at state 1, it is the reference state, and it is unmixed. So I'm going to mark this as unmixed because this is the important part. And then we introduce state 2 is mixed and in solution. And then what we're going to do in the integration, we want to integrate for the ideal system first, and then for the real system, and then take the difference. So for the ideal, so let's say the ideal. So the ideal system here, I'm going to integrate. I will get GI bar minus GI 0, and the GI bar is ideal here, is equal to RT ln of xi. Reason that I have ln of xi is that the integration gives me ln of fi hat divided by fi from the integration. But we know that let me write it down here. I just clear the page. We know that fi hat is equal to xip and fi is equal to p for the this is the unmixed state, which is right here, and this is the mixed state, which is right here, and these conditions here apply for ideal system. So that these are the limits of the integration and the fugacity for the ideal system. I can do the same thing for the limits of integrations of the real system. Will be just from the unmixed case, which is f sub I, to the mixed case, which is f sub I hat. So let's do that here, and we'll do it for the real case. So for real, so I have GI bar minus GI 0, so the same reference state, and this will be equal to RT ln of fi hat divided by fi. Now if I just subtract from the ideal, so let me write the ideal here and subtract. The ideal, we had GI bar ideal minus GI 0 was equal to RT ln of xi. Now if I subtract the left-hand side from the left-hand side and the right-hand side from the right-hand side, what do we get? We get now the difference between GI bar and GI bar ideal, which is the axis. So I'll have here GI bar minus GI bar ideal. This is GI excess bar because it is partial molar, and the subtraction of the right hand side will give us RT, and then I have ln of fi hat divided by fi times xi. So the result that we have here is very interesting. It tells us that the excess Gibbs free energy of an element in a mixture is equal to RT times the log of the ratio. Let me just remove myself here for a second. Is the ratio of fi hat over fi times xi. I can write this, so let me just expand on this a little bit to write it down. So I have here, let's say it will be GI excess is equal to RT times the natural log of the ratio, and I'm going to write it in a specific way. This is fi hat over fi on the top divided by xi on the bottom here. So note that I wrote it in such a way that I wrote it in this way, so that the ratio of the fugacity in solution to the fugacity of the unmixed state is normally, if it is ideal, this ratio should be just the fractional concentration, xi. Okay. However, if there is deviation from ideality, this ratio fi hat divided by fi is going to be different from xi, and therefore that ratio is going to give us an idea about what we call the activity of the element in solution. And for the first time now, we're going to define the term activity. Remember that ratio before, when we were talking about gases, we defined the fugacity coefficient phi sub I hat in the mixture. And here we're going to define another term that is equivalent, that's called the activity coefficient. So let me define it here and remove myself. So as I have here, the activity coefficient is going to be defined gamma sub I as equal to f sub I hat divided by xi f sub I, and this is defined as the activity coefficient. So it is an indication for the deviation from ideality. And here we would know that if we have ideal solution as an example for an ideal solution, then we would know that gamma I must be equal to 1 and gi excess must be equal to 0, and fi ideal in solution is just xi times fi. And I'm going to highlight this last point here, that if you have an ideal solution, then the fugacity in solution is just equal to, see here, what I'm showing here, that this is the fugacity in solution for an ideal system is equal to its molar fractional concentration times the fugacity of the element in the unmixed state, which is not in solution. So if you remember, if it is ideal gas, for example, F sub I would be just the pressure, and therefore X sub I times P will be the corresponding partial pressure of the system. But if we have a general system now, then we just have to use the fugacity coefficient, and the fugacity coefficient here is given by this ratio. So this ratio here defines the fugacity coefficient in solution. So let's continue on now to say that what happens when we mix elements together, and that's the next step, is to be able to determine the activities in solution of the elements. If you have an alloy, for example, nickel and copper, each one in solution, if the solution is liquid or in solid, each element has its own activity that we can find from, say, the tables, the JANF tables, or from the NIST website. And then beyond that, we are able to write an expression for the excess Gibbs free energy and relate it to the activity in solution. So in practice, if you look at the tables, then once you know the excess Gibbs free energy, if it is given as a empirical polynomial, for example, in the concentrations of the species, if you have species 1 and 2, for example, copper and nickel. So it's given as a polynomial, and the concentrations and then the coefficients of the polynomial have functions of temperature. Then once you have the excess Gibbs free energy, then you can use the previous equation to find the activity in solution, and therefore you can use it to determine the equilibrium by calculating the fugacities. And I will talk about an example in a minute. So let's continue this for a little bit here. So if I have we define now the log of, we have log, natural log of the activity of element I that we are interested in is going to be equal to G of the element I excess, and this is bar here, divided by RT. And therefore we can use this to relate the excess Gibbs free energy to the activity, and vice versa. So what happens is that if we have a solution, then generally a solution of two species, for example, let's say copper and gold, then you have the excess Gibbs energy is just the sum of xi g excess of species I, which is RT, just the sum of xi ln of gamma I. So that's from the analysis that we have pursued. So if you're given G excess, then you can find the corresponding gamma for each element. However, in practice, the G excess is given as some polynomial of the products. For example, if we have A and B, then we have XA times XB times a function of A and B, and this function is called the interaction function, and the interaction function is generally written as a polynomial. So omega AB is usually written as a polynomial from 1 to n of a coefficients that depend on the temperature times the concentration of one of them raised to the power I, etc. So these are all from the thermodynamic properties from which we are able to calculate the excess Gibbs free energy and hence the activities. So let's kind of summarize what is the procedure now for studying equilibrium or determining the phase diagrams of a complex alloy. I'll just go through an example of, say, tungsten and iron, and how we would conceptually compute the equilibrium between the tungsten and the iron in liquid state and also in the solid state, and how concentrations will split between the two different states. So let's just pursue this example. So in this example, I'm going to now we have an alloy example. So we have an alloy, and this alloy is tungsten and iron. And now I want to calculate, the first step for me is to calculate, well, the objective is essentially to find the equilibrium between these two in the liquid state and the solid state. So let's say calculate the fugacity Fi from the thermal properties, thermal props. And how is that? We took the integration from a reference state, F star, is equal to 1 over RT times GI minus GI from the reference state. And do this, I is tungsten and I is iron, and do that for the both of them. And then step 2 is that we're going to find the activity coefficients. Which is a difficult step usually, but we need the gamma of the tungsten and the gamma of the iron from the excess Gibbs free energy, partial molar, and I here is either iron or tungsten. And the excess Gibbs free energy partial molar is, as I mentioned, is written as a polynomial, let's say, of x of tungsten, x of iron, and this x iron, x tungsten, times interaction function between the tungsten and the iron. And the interaction function is a polynomial, as I mentioned before, Li of t, x b to the power I from I to the n, and hence we are able to obtain the activity coefficients. The next step after obtaining the activity coefficients is step 3, is that we want to find, now if I'm studying, so if I'm studying the equilibrium between the liquid state and the solid state, then I have to find the activity coefficients in the solid state and the activity coefficient in the liquid state. If I'm studying a chemical vapor deposition, which is equilibrium between the vapor state and the liquid and the solid state, then instead of the activity coefficients, I have to find the fugacity coefficients of the tungsten and the iron. And that's what we'll do in the next step. So we want to find the fugacity coefficients in solution, and this we obtain it either if it is gas phase, then we can obtain it by integration from 0 to the current pressure of the compressibility of element I minus 1 dln of pi. And we can also, if we don't have the gas phase compressibility, we can obtain from thermodynamic properties, which is usually the case. And then now the next one is step number 4. Step number 4 is that for a given P, given pressure, then we solve for equilibrium. Solve the fugacity of element I in phase alpha in solution is equal to the fugacity of the same element in the beta phase in solution. So that gives me a set of equations, and the set of equations, we have only 2 equations to solve, and the 2 equations will give me like a generalization of Raoult's law in this case. So we're gonna for non-ideal gas mixtures, let's now the last step that we have is, which is step 5. So step 5 is that generalize Raoult's law. So this will give me, if I have gas phase is in equilibrium with solid phase. So in this case, I have for the gas phase Y of the tungsten, the fugacity of the tungsten in solution times its pressure equals to the concentration in the solid phase times the activity in the solid phase times the fugacity in solution in the solid phase. The fugacity, this one here, the fugacity not in solution, BW here, of the tungsten, because we have just the fugacity in solution is equal to gamma times the fugacity of the unmixed state. And also we saw for Y concentration of iron in the vapor phase times the fugacity coefficient phi of iron in the mixed state times P is equal to the concentration of iron times the activity coefficient of iron times the fugacity of iron in the solid state. And in addition to these two equations, we have actually, if you look at it, we have in these two equations, we have four unknowns. We have Y tungsten, Y iron, X tungsten, X iron. So we need two more constraints, and the two more constraints are that the sum of X tungsten plus X iron is equal to 1, and Y tungsten plus Y iron is equal to 1. And hence I will be able to compute all of the concentrations in the alloy as if it is in equilibrium between the gas phase and the solid phase. So to summarize here, that we have introduced a few concepts, and these concepts are the activity coefficient, which describes the ratio between the fugacity in the solution divided by the fugacity in the unmixed state of the pure element, and that ratio is now related to this gamma coefficient is e to the g excess over RT, and g excess is obtained from thermodynamic data by fitting, and it's usually fit to equilibrium data and given to us as a polynomial from which we can compute the activity at a given temperature. In some cases you can find the activity directly. In some other cases you can convert the excess Gibbs energy to the activity, and hence you're able to determine the equilibrium. Remember, the equilibrium is always, has been, the equilibrium is the equality of the chemical potential. But when they are in solution, the chemical potential in solution is equivalent to the fugacity in solution. So you get the hat on top. And therefore, you have to have enough equations for each element to equate its fugacity in solution in phase alpha to phase beta, and you proceed with the solution as outlined here in this lecture. So we'll finish the lecture at this point, and in the next step we will continue to study a little bit more about phase diagrams.